Okay, hi. So before we start, I have a confession to make. I really hate going to the store. And it's really hot outside. I'd much rather stay at home, turn the AC on, do my shopping online. But even when I do that, things can go wrong. Like in this example, posted by the comedian and writer Hagit Ginsburg. She was buying groceries online, and she got one of those messages, which I guess all of us got at some stage, telling her that one of the items that she ordered was out of stock, and she needed to pick a replacement item. And just in case it's not super obvious to everyone, those two things are practically identical. Okay, and this was a couple of months ago. It was the beginning of summer. Hagit was busy with her children's summer vacation. She really doesn't have the time to tell Shufersal to replace, the cottage cheese with the same cottage cheese. And the truth is, when something like this happens, it really harms user experience, right? And the effort to try and prevent those things from happening by identifying those two entities, those two replacement items, represent the same real-world object is most often referred to as an entity matching problem. And entity matching is by no means unique to the world of grocery shopping. It's relevant to a variety of fields, from medicine through law, all the way to commerce, and it really is a problem that practically everybody deals with. Right, so before we describe how that problem looks on our end, let me introduce myself. So I'm Nati. I'm an applied researcher at eBay. I work in our Israeli R&D center located in Netanya. I have about 10 years of experience working on really cool data science challenges in a wild variety of fields, from neuroscience through education, all the way to e-commerce. And as I said, all of those domains deal with entity matching problems on different scales. But when it comes to eBay, we work in a huge scale. Okay, we have about 2 billion live listings. We have more than 130 million active buyers searching through those listings on a daily basis in 190 global markets. That's a lot of data to take in. And in addition to that, one important thing to remember is eBay is very much concerned with C2C commerce, right? It means that it's not professional stores, it's people like you and me trying to trade with each other, and that fact is going to be important in a second, so we'll keep that in mind. All right, so let's maybe start simple. Let's say that I have this shoe at home, and I want to sell it on eBay, right? So how would I do it in an ideal way, in an ideal world? I'd go online. First thing, I'll upload a really good photo. I'll provide a descriptive title. I'll give important features like the brand and the model. I'll even provide an MPN, which is basically a code that uniquely identifies the shoe that I'm trying to sell, and everything will be perfect. But as you can probably guess from the fact that I'm standing here today, that reality is a lot more noisy. Sellers often use slang in their listings, like RTR instead of retro. They provide irrelevant information to the type of shoe that they're trying to sell. They provide wrong or even contradicting information within the same listing. And as the average person, I don't necessarily know what an MPN is, right? And let alone be able to find it and correctly provide it in the listing. And that really creates a lot of issues for everyone, because now, as a result, potential buyers will have a much harder time finding this great shoe that I'm trying to sell, and as a result, I'll have a harder time selling it, right? And if you remember, we're a C2C business mostly, so that means that the vast majority of listings on our website look like this, right? So this problem really lies at the heart of what we're trying to do at eBay. So what can we do? How can we deal with it? Luckily at eBay, we maintain a catalog of all the different shoe products that exist out there in the world, and if we could match one entity, in our case this shoe that we're trying to sell, to another entity, in our case the correct product that it represents in the catalog, then we're golden, right? Because now I can use the catalog information to do all sorts of really good things, like complete missing information, identify the details are wrong, maybe even correct them, and then everything will be great. But really, I didn't solve the problem yet. I only pushed it forward a little bit, right? Because now I need to somehow use the noisy information of the listing to figure out which out of the millions of different products that exist in the catalog is the correct product that I should match my item to, right? So we need a really good entity matching solution. And we require a lot of things from our models, but primarily speaking, there's two main metrics that we're trying to optimize. We have recall and we have precision, So let's take a short moment to remind ourselves what those two things mean. So for recall, given that the item that I'm trying to sell really does represent a product that exists in the catalog, what is the probability that our model will be able to match it to that product? And on the other side of the coin, we have precision, where given that our model predicted that the item should be matched to a specific product, what is the probability that that prediction is correct? And those two metrics live in tension with one another. Generally speaking, the more conservative our model is, the better its precision will be, but usually at the price of losing recall. And ideally, we want to somehow optimize both. Or in other words, we want to increase recall without compromising precision. Right. So in order to achieve that, we developed a deep entity matching framework, which consists of 2 steps, which I'll discuss in a second. But as a whole, it works like a funnel. So we start with the item potentially matching any of the millions of different products in the catalog, and then we gradually narrow it down from millions down to a few dozens, and then all the way down to a single match. Right? So let's look at the steps and see how they work. The first step, called retrieval, prioritizes recall over precision, and it is relatively computationally cheap. It works by taking the item's title and features and comparing them against an index of all the different products that exist in the catalog. In our case, we use the BM25 ranking function in order to score each product according to its relevance to the item at hand. And then by taking the top scored candidates, we effectively narrow down the search from millions down to a few dozen likely candidates. Right? And so for the sake of intuition, because I showed you we're dealing with a Nike shoe, for example, I probably don't need to consider candidates from other brands. So for example, New Balance, right? And also because we prioritize recall, we don't really care if the correct product is ranked first within that list of candidates, only that it exists within that list. Now that we have a few likely suspects, we can push them to the second step called matching. This step prioritizes precision over recall, but at the cost of being more computationally expensive, right? So we use a transformer-based language model in order to compare the item to each of the product candidates that we received from the previous stage and assigning it with a score between 0, representing a complete mismatch between the item and the product, or 1, representing a perfect match. Right? So effectively, by running our item through this entire pipeline, we did exactly what we want in the beginning, right? We narrowed it down from millions to a few dozen likely candidates down to a single product that either represents a match or a mismatch. Right, so maybe to better understand how this matching part works, let's look at a simplified example. So we start with the item's title and features, and we use the following strategy in order to turn it into a sentence. We use special tokens to denote the feature names, followed by their corresponding feature values. Right, so now we have a sentence. Now we use the exact same strategy to construct a sentence for the product candidate. And we connect those 2 sub-sentences together using a special separator token. So now we have one long sentence that represents the pair. And now we take this one long sentence and we push it into the language model, the trained language model, which calculates an embedding vector. This embedding vector is in turn pushed into a classification head, which gives us a final score between 0 and 1. Right? So if we go back to our original shoe, and imagine how its scores might look like, right? So if we take the correct product, it will receive a score that's really, really, really close to 1. And remember that it's not exactly 1 due to the inherent noise that existed in the item's description in the first place, right? If we take another product that's really, really similar, it has the same brand, the same model, but it contains other secondary features, like its color, for example, then it will receive a score that's significantly higher than 0, but is not the highest one on the list of candidates. And just for the sake of example, if we take a shoe candidate from a completely different brand, it will receive a score of practically 0. Okay? Perfect. So we developed this entire pipeline. It looks great, it makes sense, but how do we actually know that it works? So of course we conducted experiments, and we did that by using 4 relatively small data sets, each containing about 10K human-judged samples from a different category. And then for each of those data sets, we trained our model and we compared it against a baseline method that uses an exact matching scheme to compare the item's features to those of the product. And in order to evaluate how well our model did, we calculated something called the recall game. So let's maybe, again, take a second to understand what recall game means. So given a test set from a specific category, we push it into the baseline method, into the exact matching method. This baseline method gives us predictions that are either correct, in which case we're not really interested because those cases are so easy that exact matching can solve them, or it gives us incorrect predictions. Those incorrect predictions represent hard cases that we want to work on. So we take those hard cases, we push them into our own model, into our own pipeline, and we activate it at a precision level, and that's important, at a precision level that's equivalent to the precision level at which the baseline method works. So we maintain the same precision as we had before. And then we take those predictions that came out of our model and we calculate the recall over that. So you can see the results here, and of course, depending on the difficulty of the data sets, because not all data sets were created equal, we can gain a recall of anywhere between 40 and even surpassing 80% on the hard cases. And again, remember, because we activated our model at the same precision as the baseline method, we increased recall, but by definition, without compromising the existing precision, which is exactly what we wanted to achieve. Right? So, great. We're better equipped to deal with the problem. Now buyers will be, have a easier time finding the things that they want to find, and as a result, sellers will be able to sell much more easily. But it turns out we actually gain a lot more than our initial intention, right? Because now, since we can link correctly between the items and their corresponding products, we can calculate all sorts of aggregations and provide statistics to our users to make their lives even better, even better still. So we can provide things like price guidance to both buyers and sellers, because we know for a given product what the ranges of prices that we see depending on different features. We can give signal about availability and even future release dates. We can help our users narrow down their search by focusing on important features. We can relate the catalog from a specific category that we're working on to other categories and then provide recommendations for accessories and whatnot. We can compare our item to other competing brands or whatnot. But we can also compare the shoe to other shoes that maybe serve the same purpose, running or playing basketball, whatever it is, right? So that's it. I hope you're convinced that we've seen a simple and effective entity matching framework. It requires relatively little data to train, especially in the age of LLMs, which use a lot more data. I hope you're convinced just from looking at the architecture that it wasn't specifically designed for the world of e-commerce. It can be applied to a variety of domains to solve entity matching, practically anywhere. And actually, its performance can be boosted even more than I showed here today with all sorts of really cool and interesting techniques. But due to time constraints, I couldn't go into them today. So if you're interested, please come visit us at the booth and we can discuss it further. Thank you very much.